Greetings, everyone. This is Jeff Wilkerson, Professor of Physics at Luther College, bringing you the next in our series of what to look for in the night sky. We're talking about the week of July 31st, 2023, so really the first week of August. This time around, it's a full moon week. This moon starts full right at the beginning of the week and wanes away as the week goes on. So there's going to be a lot of moonlight impacting what you might want to observe this week. One good thing with the moon, it passes right underneath Saturn on the night of August 2nd into the morning of August 3rd. So Wednesday night into Thursday night, you'll get a chance to see the moon still nearly full, 97% full, I think, or so on that evening, just below Saturn. So be sure to get out and check that out. Otherwise, we want to look at stars because that full moon is going to wash out nebulae and clusters and galaxies and things like that we sometimes look at. So we're going to focus on the constellation of Aquila this time around, and this part of the summer triangle Altair is. So Altair is the brightest star there. We talk about the summer triangle from time to time. I'm not sure we've spent a lot of focus on the constellation of Aquila itself. So the brightest star, Altair, there is about 0.8 magnitude, very bright. Remember, this magnitude system counts backwards. The smaller the number, the brighter, and every step in magnitude is a factor of 2.5. And so right next on either side of Altair, you've got Tarazed and Al-Shain. These are all Arabic names for the entire groups of stars in this region. And so you've got these fairly bright stars right next, but I like to think of Aquila as looking like a flattened diamond, if you will. And so it can look down this direction like a sort of a diamond shape that's squished that way. It looks like a kite or a stingray, maybe, and the tail of the stingray would be back down this direction. And so from the three stars at the top, if you will, here, it depends on what time of year it is, what that orientation actually looks like. You've got Zeta over here, a 3 magnitude star, third magnitude star, Theta down here, a 3.2 magnitude star. So two pretty good bright stars. You see down, remember, fifth magnitude or so under most dark skies if you don't have a lot of light pollution. And at the base of the diamond is Delta, a 3.4 magnitude star. So all pretty bright stars. Lambda is a 3.4 magnitude star forming the tail of the stingray down this direction. So this is a nice group of stars. Good time with the moon bright in the area. It's well placed this time of year. It's up as it gets dark. It stays up all night, basically. So a good time of the year to explore this region of the sky. Remember, this is the southernmost star in the summer triangle. So if you see Vega and Deneb up north, you swing down to the south and you come across Altair down here, and then look for this diamond shape with the tail trailing off below it down here. Now, between Theta and Delta is a very interesting star, Eta. The Eta star in Aquila is a Cepheid variable star, and the Cepheid variable star that varies in magnitude from 3.7 to 4.5, roughly speaking. So it's about 2 times brighter at its brightest than it is at its faintest. And it's a great variable star because Cepheid variable stars can have a pretty wide range of periods. But this one has a period of just over 7 days, 7.1 days. So in a week, you can see it go from faintest to brightest back to faintest. So it's actually going to start this week ahead. This is a great week to be observing this. And it's a big bright star. You can see this with your naked eye. And so you can see various stars around the area that you might compare it to try to, so identify this star, sketch it, take a picture with your cell phone, do something along those lines, identify Eta in here, I'll draw a line from Theta to Delta, and it's a little less than halfway, 40% of the way, let's say, from Theta over to Delta. Right on that line is Eta. So you should be able to locate it that way, and then watch it get fainter as the week goes on, and then get brighter toward the end of the week. Now, it has such a short period, in about 7 days, you can't miss many days, or you'll lose the pattern of brightening to dimming. But with these good stars, lying right in between these two brighter stars, you should see it. It's fainter than these two stars, but you should see it get quite a bit fainter as it fades away and then brightens back up toward the end of the week. So somewhere in the early morning hours of August 6th, it should be back at full brightness. So as the week starts here ahead that we have, it's going to get fainter and fainter and get brighter and brighter. Now these stars, Cepheid variable stars, that period of how long it takes to get from brightest to dimmest back to brightest is related to how intrinsically bright the star is. And if you know how intrinsically bright a star is, you know how far away it is. We like to write the formula to say the distance in parsecs is equal to 10 to the power of a parrot. How bright the star appears on the sky, that's this number we've been talking about, minus how bright it is intrinsically, the magnitude, how bright it is in the magnitude system, plus 5 over 5. Now that doesn't take into account dust and gas scattering light out and whatnot. We have to deal with that. It's hard. But in any event, this tells you can calculate how far away a star is. So these, if you know what that intrinsic magnitude, how bright the star is intrinsically, you know how far away the star is by comparing it to how bright it appears right here. This idea that the period the time it takes to get from brighter to dimmer back to brighter, for a Cepheid variable star was discovered by Henrietta Leavitt about 100 years ago. So she was looking at stars in the Magellanic Clouds and figuring out these variable stars, how bright they were, was very strongly related to how long it took them to go through this cycle. So for example, you can see a sample variable star. You know, a Cepheid variable star might look something like this, as you see it get brighter and dimmer and brighter and dimmer here. And so you might see that going bright to dim to bright over the course of this one I have drawn. I just drew this one by hand. Over the course of about 5 days. And we're talking about 7 days for Eta Aquilae. And so then you can look at this and you can actually derive a relationship for how bright these stars are. So you can take the stars, you can make a table of data that says, here's how bright the star appears to be. This is again from Magellanic Cloud variable stars. There's the period in days ranging from 2 at the top down to 28 down here at the bottom. And you can graph that data. And that data is taken from Butler's Astronomy and Astrophysics Supplement, number 32, back in 1978. And if you plot it, you get a relationship that looks something like that. You see that bold curve is a fit, a functional fit through the data points that were in that data table taken from this Astronomy and Astrophysics Supplement that we were just looking at in the table. And so you see the nice clean relationship that you can use to then find the period magnitude relationship for these variable stars, and you can find distances. And this is how, for example, when Edwin Hubble first found a Cepheid variable star in the Andromeda galaxy, we learned that this was an external galaxy using Henrietta Leavitt's prior work at that time, work of just about 10 years earlier. Using her work, he was able to say, oh yeah, her work that looked like this, right? To say, I can use that relationship to show that the Andromeda galaxy's got to be a couple million light years away. There's no way it could be inside the Milky Way galaxy. And so we start to unfold the distances in the universe. The universe grows for us in this way. So this is what we want to think about. We want to go out this week and we want to observe the stars of Aquila and identify them all, recognize zeta and theta and delta and lambda, and find all of these stars in here and make sure we can see them. And then when we find Eta, let's watch it for a few days and see if we can watch it getting dimmer as we get toward midweek, and then as we get toward the end of the week, coming out of that, headed back toward peak brightness. From one night to the next, it's going to change brightness enough that if you're paying attention and you're really doing close comparison with theta and delta, for example, you will be able to see how much that brightness has changed. So I hope that's a fun observing project, pretty self-contained. If it doesn't work this week, you can do it next week or the week after. Do it anytime the rest of the summer, because this constellation's up, Aquila's up pretty good for us the rest of the summer. And you can, with this thing contained within a week, a period like this, if you get a string of 3 or 4 or 5 bright, clear days in a row, you're going to be able to really map this brightness changing. And I think it'll be a fun project for you. So go on, give it a try. Good luck with it, everyone. Also, don't forget on the night of the 2nd into the morning of the 3rd to watch the nearly full moon slide below Saturn. And that'll be a really beautiful pairing. And I hope you have a great week, everyone. And as always, thanks for watching.